you can see that what happens is the ice will catch on fire because there's a bunch of methane that's trapped in there. And so a lot of times, like when they're digging for gas and stuff like that, they'll find some of these. So, you know, some oil people or whatnot, you can go through and be like, hey, can I borrow some of this ice? And it'll just catch up like nothing. So that's kind of a crummy picture. Let's see if this one looks a little bit better. Yeah, right. So that's what's happened in this system is you have the like water molecules that form its ice lattice, and then there are just some methanes that are stuck in there. And then you sometimes have added effects, like you couldn't catch water on fire normally, but thanks to having methane incorporated in there, you could do that. And it burns at a much lower temperature too, which is nice. So co-crystals are kind of, sometimes they just happen. Like in my research, we look at them to try and make extended networks. We're trying to make two-dimensional, really thin, like one molecule thin wires. And so by having different molecules, you get some properties. So if you have a proton donor, a proton acceptor, you can actually build a wire out of that, which is kind of cool. So those are like the main things that people discuss when they're talking about structure of solids. Are there any questions about that? No? Okay. Let's start to talk about the electronic structure of these solids. So as chemists, we always tend to really care about where the electrons are, and if we understand that, we know the behavior of the system. We're going to talk pretty in depth about the electronic structure of solids and additionally metals. So that's where we're heading next. So we're going to recall some things that we discussed in lab. So the next area we're at is electronic states and solids. And we're going to look at a simple example. We know in molecules we have discrete energy levels. So we have discrete energy levels. However, in solids, we reached a point where we have so many of these molecular orbitals or atomic orbitals that overlap, we get to a continuum of states. So in a solid, we have a continuum. Continuum of states. And this is what's known as a band. So we're going to first consider rings of hydrogen. Rings. It's a pretty simple spot to start because how many electrons does hydrogen have? One. In PChem, when we start to talk about the atom, we always look at hydrogen first because it's the simplest system. Okay. If we consider just H, what's its electronic structure look like? Or what orbitals do we have? Yeah, we got a 1s. Okay. How many electrons are there? One. Yeah. Okay, then let's look at H2. So we incorporate two of them, their atomic orbitals overlap, we get new molecular orbitals. What are those?
Like a sigma and
Yep.
a sigma star.
Yeah, we get a sigma and a sigma star. Sigma, sigma star. And then we have 2 electrons in that sigma, right? If we were to draw out kind of like a schematic representation of this orbital, you would have 2 wave functions that are in phase with one another. What about for this one? What would change with those wave functions? Yeah, so one would be negative and one would be positive. So the sign change happens. Okay, what about H3? And when I say H3, we're talking about a system. I should have left more space. I'm going to move it out a little bit. We're talking about one arranged in like a 3-membered ring like that. Well, we're going to get a situation where they're all bonding with one another, right? So we'd have that, right? What's another, so how many molecular orbitals do we have to have? 3, yep. We're going to get another situation where we have anti-bonding along somewhere along here, so let's color that one in like that. And then we're going to have another system that ends up being the same energy. That's like that, right? So we've just changed those 2 positions. So now we have this. How many electrons do we have in total?
3.
Yeah, so 1, 2, and then there's going to be one that goes somewhere up there. That's really unfavorable to happen though, right? You know, it likes to be at H2. We're just pretending, okay, if we had H3, what would it look like? Okay, if we go to H4, talking about a system that looks like that. We're going to get one where they're all in phase with one another. What are other possibilities that we could have? Or what is going to be the highest in energy, the worst case scenario?
Every other.
Yep, every other one. So we can have one up here or every other one. So like that, right? What other cases could we have? Well, remember each energy level that we go up, we have to introduce a node.
They're right next to each other.
So we could have one, yep, where they're right next to each other. No, there are actually 2 of those. So there'd be one that looks like this. Like that. And then another one. We got colored different ones. Oh, wait, do we have it? That one. Let's do that. So we're going to have 4 electrons in this case. 1, 2, 3, 4. Okay, if we're going to move to one that sort of looks like benzene, we're going to look at H6. Where at each one of the points, we have a hydrogen. There we go. So we're going to get one that's really low in energy, right? And that's where all of them are in phase with one another. Which one's going to be the highest in energy?
There we go.
Yep. Again, every other one. Like that, right? And there are actually a couple nodes along here, so let's try to get them. Nope. 1, 2, 3, like that. Okay, and then we're going to have a handful of them. 2, 3, 4, 5, 6, and 2 more like that. When we go to this one, we're going to have to introduce a node. There's going to be a node that goes along there, so all of these are going to be in phase with one another. Then we have another one like this. Or in this case, there's a node along here. We're actually not going to have any contribution from either of those. So it looks like that. And we'll have another one for these other two. Let's try to draw them. So now, these ones, we had one node. How many nodes do you think we have to have for these guys? 2. Yep. And where do you think they're going to cut through? Should-
Top and bottom?
Yeah.
Yep, so we're going to have one that goes through like that. So then we get those, these are alternating. And then we're going to have another one that kind of cuts along here. Okay, so as we keep adding atomic orbitals, we just keep getting more and more molecular orbitals, right? There's eventually going to be a point where, let's say we look at H infinity. So we're talking about one where we have just a ring of hydrogens slapped on itself going back over. What we'll eventually get is something like that, where I'm drawing discrete energy levels, but in reality there's so many packed in here that it's hard to tell where the states actually are. And we represent that sometimes as a continuum like this. But we have something called the Fermi energy that is here, or EF. These are the occupied states, these are the unoccupied states. As you go up in energy, you're getting more anti-bonding. So the bonding orbitals tend to be down here, non-bonding are somewhere along here, anti-bonding are way up high. So that's what the band is. How are we doing? Okay, let's talk about the 1D hydrogen chain real quick, and then we'll move on and be done for the day. How's that sound? Good? Okay. So we're going to start with a simple system. We're going to look at a one-dimensional hydrogen chain. 1D hydrogen chain. So we're going to assume we have a one-dimensional hydrogen chain that extends for infinity. Assume we have an infinitely long one-dimensional chain of hydrogens that is evenly spaced. That are evenly spaced. With a distance of A. So A is the distance between each of the atoms. Between each atom. So what we're talking about is okay, this is our first hydrogen atom. Next, there's another one, and this distance right along here, that's A. But it extends on forever. So on each one of these distances, that's A, and that's A. So they're all equally spaced apart from one another. Well, what would we expect? Like, let's say we had an infinitely long chain of hydrogen. What would we expect it to happen?
Probably something.
What's that?
Why don't we try to make like something so it wasn't just fall off?
Yeah, it would try not to be that way, right? What does hydrogen always want to try to become? Yeah, it wants to try and become H2. So we're setting it, so in reality, if we built this system, we had no pressure on it, bam, it would just break apart into H2. However, we're just gonna set it up as a hypothetical system for now, to learn some stuff. And actually, this is how hydrogen behaves at really high pressures. It actually behaves as a metal. And it's a superconductor, it's predicted to be a superconductor. So on Jupiter, there's superconducting hydrogen that hangs around, which would be awesome if we could harness someday, because then we'd have a superconductor. And can you guess about the cost of the most plentiful element in the universe? Pretty cheap. So, some nice stuff there. Okay, so we know that this doesn't exist. We know this system does not exist at ambient temperature and pressure, and the chain would decompose into H2, right? And the mechanism by which this would happen is it would start to squeeze, it would get distorted. This is known as a Peierls distortion. I think that's how you spell his name, which doesn't look right, but it is. And this is what physicists refer to it as. Chemists would call this a Jahn-Teller distortion. So physics or a Jahn-Teller distortion. In chemistry. The reason we're doing this, we're using this as a simple exercise to try and understand some things about the solid state nature of systems. Okay, so next time we're going to talk about the different electronic states that arise from having a periodic system like this, and then we're going to be looking at some very limited mathematics, but eventually we're going to get to a point where we're going to look at something called band structures, where we have this energy, K space, and you get something like that. This looks like it doesn't mean anything, it looks like a simple line, but to a trained chemist or physicist, there's actually a lot of information that's there. So we'll discuss that next time. Are there any questions? No? Okay, you guys got your assignment? I'll have these graded and ready for you hopefully by the end of today. All right? The other stuff's graded. It's just getting that. We gotta find where to put James' stuff too.